Hi everyone, so I've got life cycle of a star very briefly. I've got magnetism and electromagnetism, electricity and radiation. These are some requests that people have made. I also have some sort of bonus questions at the end. So without further ado, let's go ahead and jump into the video. I'm going to take you through those 4 topics. I'm going to do it quite quickly. If there's time, then please do ask for any bits. Please do ask for any other requests. If I think I can confidently go through it then and there, then I will. As I said, we've got these different topics. We've got the life cycle of star. We've got magnetism and electromagnetism. We've got electricity, and we've got the medical part of radiation. So it's alpha and beta and gamma for the medical uses of that. I'm going to use the AQA spec basically to go through it. That's because that's the most common one. But this is so similar. You will notice, I'm sure, if you are doing OCR, if you are doing Edexcel, if you are doing Eduqas, then you will notice how similar this stuff seems to yours. It is really that close. So do not think to yourself, this is the wrong specification for me. I teach OCR mainly, and this is just exactly the same. There is maybe 1 or 2 different things in what they expect you to be able to do, but this is basically exactly the same. Earlier on today, I did a little introduction of why you're not going to fail and how to make sure that you're revising effectively. And it's all about metadata, metacognition. So do think about how you're learning different things and why it's going well or not. And then I also did a little live stream about that black hole image that has just come out recently, and how that can be some of the hardest questions. Is those things there. So this little point here, yes, I will go through Fleming's left-hand rule. That's going to be coming up in this as well. Yes, every single grade is still realistic. There is still time. That's something that I did in the live feed the other day. Yeah, with transfer of EM waves, I think that will come up in a little bit, but if not, then ask at the end. Let's jump into the visualizer because it's time to go. Okay, so this is life cycle of star, right? So a life cycle, star goes through a life cycle. The life cycle is determined by the size of the star. Now we were talking about this is why I started with this one. We were talking about this because we've just taken a photograph of a black hole, the first one ever, and we were mentioning that. And that was 600 million times bigger than the sun, okay, which is a massive thing. So you should think about it as having 2 branches, the sun-sized star and a more massive sized star. It starts off exactly the same. Now I did this in a video just the other day as well, a live feed just the other day as well, so I'm not going to spend a lot of time on it, but I just want to point out just a couple of things, because this is the exact same diagram that I drew. These are the different steps that you need to memorize, but the harder questions are how do you get from this point to this point, from this point to this point. So it's memorizing the detail around this that's going to make sure you get those marks. So this first one, how does the cloud of gas and dust get to form a protostar? Well, gravity brings it together, friction makes high heat and pressure, and then you get fusion. Okay, and it needs to be fusion, okay, nuclear fusion, F-U-S-I-O-N, and you need to spell that correctly. And the reason why you need to spell that absolutely correctly is because if there's any dubiety of whether it's fission or fusion you're trying to spell, then we're just going to mark it wrong, I'm afraid. Okay, now a main sequence star is when there's enough fusion and there's enough matter for there to be a balance of forces between the radiation pressure outwards. Okay, that's the force pushing outwards because of all that fusion, and that has to be the same as, has to be equal to the inward gravity. Okay, so once you've got those 2 forces balanced, then you have a main sequence star, and that's why they're those perfectly neat little ball-shaped things. Okay, if it's got about the same sort of mass as our sun, then it's going to expand and cool and become a red giant. Then fusion is going to start to slow down. The layers of all those different elements it's made drift into space. Okay, and you get, eventually you're going to end up with a white dwarf, and then finally all fusion is going to stop, and it's going to no longer give out light, so it's going to be a black dwarf, or often called a brown dwarf, but surprised they call it black dwarf in this spec, to be honest. If it's got more mass, then it becomes a red supergiant, so still expands and cools, red supergiant. Then it will collapse in on itself, okay, and you don't need to really know that, but you need to know that it can explode as a supernova, and in this point heavier elements are made. And two options are middle-ish mass, a neutron star, which is an incredibly dense ball of neutrons, and here a black hole, which is what we were talking about in the video earlier, which we don't know what it is really, but it was when it's got so much mass, it becomes an incredibly dense point in space, which has got so much gravity that light can't escape it. So let's see some other points that they need us to know. Fusion process stars produce all the naturally occurring elements. Elements heavier than iron are produced in a supernova. So you need to know that. You need to know that heavier elements than iron are made in this supernova. Okay, so there must have been a supernova star, a more massive star in our region of space, which distributed these elements throughout our region of space, because there are elements heavier than iron here on Earth. Now actually we would have been formed after that supernova, and all of that material would have been scattered throughout space, and eventually started spinning again, and a new star produced in the center of it, that's our sun, and that all of those elements would have been separated out into what we know as the planets. Okay, students should be able to explain how fusion processes lead to the formation of new elements. Well, basically what fusion is. Okay, fusion in its simplest form is hydrogen plus hydrogen, okay, making helium, okay, fusing together to make helium basically. Now normally, this is the simplest form, this is less likely, this is proton plus a proton. Normally you've got deuterium and tritium making helium nucleus, which has 2 neutrons as well as 2 protons, plus some kinetic energy on that extra neutron that needed to be conserved over here in the nuclear equation. Okay, so fusion processes are just state it like this: light elements fuse to form heavier elements, and in the process energy is given out. Okay, I hope that makes sense to you all. Let's just jump straight in, because I know that a lot of people have been requesting this one. This is magnetism and electromagnetism, and hopefully that all made sense. If you're on a different spec from AQA, I bet that was just exactly the same stuff that's on your spec, yeah? Okay, let's jump into it then. So the poles of magnets are places where magnetic forces are strongest. When the two magnets are brought close together, they exert a force on each other. This is all you need to know. Like poles repel, unlike poles attract. I'm sure you've got that idea. That's the kind of thing you come to secondary school knowing. A permanent magnet produces its own magnetic field. Oh, sorry, these are examples of non-contact forces. All right. Permanent magnet produces its own magnetic field. An induced magnet is a material that becomes a magnet. So this is what was asked for. An induced magnet is a material that becomes a magnet when it's placed in a magnetic field. And do not get confused between induced magnetism and electromagnetic induction. Now actually the request they had was for induced magnetism. That's this basic, if I take something that's not magnetic, here's a paper clip, this isn't a magnetic thing, but if I take that and I put it near a magnet, then that becomes an induced magnet. It's a temporary magnet, if you like. So that's what the word induced magnet means. So that when it's placed in a magnetic field, it becomes a magnet. So now induced magnetism always causes a force of attraction. When removed, this induced magnet no longer is magnetic. And why is it always attraction? It's because the magnet that is producing is inducing this magnet attracts the side attracts the side to it that it is not facing it. So always you're going to get an attractive force. Now that's going to become clear when I just do these little sketches in a second, which is domain way to explain magnetism. So I'm going to talk about domain theory now, which always, if you're ever thinking, oh, this is a bit of a funny question about magnetism, then going into magnetic domain theory will really help you just explain what's going on. So you should be able to describe the attraction and repulsion, that's absolutely fine. You should know the difference between permanent and induced magnets. So this is not currently a magnet, but if I put it in a magnetic field, it becomes an induced magnet. So I like these statements in this specification, by the way. You should be able to do. So things you should be able to do are really nice. You can use them as a checklist, things you should be able to do in the exam. So if I just draw like something that is not magnetic currently, okay, now you can imagine it as just being made up of all these little magnetic domains. So a ferromagnetic material like iron or nickel has some little magnetic domains. You imagine these little arrows are pointing in the direction of their kind of north-seeking pole. Imagine these just being little bar magnets themselves. Now at the minute it's not magnetic, so they're kind of scattered and just pointing in any kind of random direction. But as soon as it goes into a magnetic field, then all those little magnetic domains, they start lining up, and that adds up to one magnet. Basically, they're all now pointing in the same direction. So now it is a magnet, it's acting as a magnet. So we'd call this an induced magnet. Now the moment that I remove that magnetic field which created that, the moment I take that away from, you know, this is if I had a magnet just like here, then the moment I take that away, then they're just going to get randomized again and it's no longer going to be a magnet. So this induced magnet basically means a temporary magnet. Okay, I hope you understand that. That's domain. Oh no, sorry. That's not domain, that's domain. Cheesy physics joke. That's domain theory, okay, of magnetism. Okay, next bit in magnetism. Okay, so magnetic fields themselves. So the region around a magnet where a force acts on another magnet is called a magnetic field. Okay, so that's fine. This is a force field. I think it's an important thing. I've got a video in the description that describes this stuff with force fields. The force between a magnet and magnet material is always one of attractions. Just talked about that. The strength of the magnetic field depends on the distance from the magnet. The field is strongest at the poles of the magnet. So you should be able to draw the magnetic field around a bar magnet. Okay, and that explains a lot of these things in here. So if I just quickly sketch that out, if I can imagine it, it's quite small over here, unfortunately. North and south, field lines looking something like this, closer together at the poles than they are around the outsides, and with lines pointing from north to south. So arrows towards the south pole, and just check that they're all going in the same direction. Okay, you notice they're parallel outside of the field in a bar magnet, okay, and they're always from north to south. So the field is strongest here, weakest here, because they're furthest apart here. Okay, the strength of the magnetic field depends on the distance from the magnet. The field is strongest at the poles of the magnet. I think we've done that now. So a diagram like this really helps you imagine those two little points, I think. The direction of the magnetic field at any point is given by the direction of the force that would act on another north pole. So you can think about the arrow as being, if you put a north pole there, it would be repelled from it. Okay, the arrow shows the direction of the force on another north pole. And if you put it here, it would be attracted to it. Direction of the magnetic field line is from north to south of the magnet. Now they say north seeking because when we talk about the Earth's magnetic field now, think about the north pole of Earth, okay, is the direction which a north pole of a magnet points. So actually the north pole of Earth is actually a south seeking pole, okay. So if you think about the entire Earth, actually this is the north pole of Earth, but it is the south pole of this giant bar magnet. That's a really annoying thing, annoying idea, I know that. If you think about our compasses, are little individual bar magnets, and they will point towards the south pole of a magnet, if you like. So you think about them as being north seeking or south seeking, it makes a bit more sense in terms of where north is on the globe. Okay, moving on. Describe how to plot the magnetic field around a compass. Sorry, the magnetic field around a magnet using a compass. You basically place the compass in different positions and you join up the way the arrows are pointing on the compasses to make lines. There's nothing hard about that. Explain how the behaviour of a magnetic compass is related to evidence the core of the Earth must be magnetic. Well, this one often is just that it always points north. Okay, at any position on Earth, a compass is always pointing towards the geographic North Pole. Okay, so electromagnetism, now this is the bit where it gets actually difficult, isn't it? So when a current flows through a conducting wire, a magnetic field is produced around the wire. That's not very good. Okay, leave that where it was. When a current flows through a conducting wire, a magnetic field is produced around the wire. The strength of the magnetic field depends on the size of the current and the distance from the wire. So this is, you know, this little diagram that you often see, and it looks pretty confusing. They have like a wire like this probably, and they have the lines going in concentric circles around the thing. Now you do need to know the bigger current, stronger magnetic field, so those lines will be closer together. And the further away you are, the weaker the magnetic field. So the lines officially should really be more spaced out the further away they are. But it doesn't matter too much. I don't really tend to worry too much about that in the GCSE. We're going to talk about shaping the thing in a minute, but you do need to be able to draw this type of field and know the direction, I think. Draw the magnetic field for a straight wire, current carrying, and showing the direction of the field. So just while I've just drawn it, okay, just while I've just drawn it, let's do the direction as well. And to work out the direction, we use the right hand grip rule. So imagine the current is the direction of your thumb, and then your fingers point in the direction of the arrows, okay, the direction of the field. So on here, I'm just going to go thumbs up like this, okay, the field's going up on the page, so the arrows are pointing in the direction of my thumb. So this, remember this one, this is the right hand grip rule. Okay, hope that makes sense. Moving on. Magnetic field around a solenoid has a similar, so shaping a wire into a solenoid increases the strength of the magnetic field by creating a current through the wire. The magnetic field inside a solenoid is strong and uniform. So a solenoid is just a coil of wire. So if you take our wire and you kind of loop it like this, then you end up with all of those little circular magnetic fields all linking together, and it forms this magnetic field. Looks something like this. It's a terrible drawing actually, one of my worst times I've drawn this thing. And you can work out the direction of which end is which, but they don't expect you to do that. But they do expect you to realise that in the middle, in the actual coil, it's uniform and very strong, so all close together. And around it, it's the same shape as the magnetic field around a bar magnet. Okay, hope that makes sense. Magnetic field around a solenoid is similar shape to that bar magnet, just said that. Adding an iron core increases the strength of the magnetic field around a solenoid. So if you add an iron core in the centre of that, then you get like double the effect, because you also get the effect of all of those magnetic domains joining up from the last bit. Okay, so it lines those up and then they add to the magnetism overall, and you get the electromagnetic effect from the thing there as well. So it just like amplifies the field. Now what you should be able to do, describe how the magnetic effect of a current can be demonstrated. So that would be by using a current carrying wire, maybe putting iron filings around it, or using compasses to show that. Draw the magnetic field pattern for a straight wire. Thus we've just been able to draw that, and we remember that using the right hand grip rule. And explain how the solenoid arrangement can increase the magnetic effect of the current. Think about it like this, the circular fields combine, okay, to form a stronger field. So I hope that makes sense. Think about this, they like this idea in the new GCSE of fields interacting to either produce forces or to make stronger fields in this case. So you should also be able to interpret diagrams how electromagnetic devices work in order to explain how they work. We have an exam question coming towards the end of the video, which you can stick around for, and there is an exam question that asks you to do exactly that. Fleming's left-hand rule then, okay. When a conductor carrying a current is placed in a magnetic field, there's an exam question coming on this one at the end as well. The magnet producing the field and the conductor exert a force on each other. Now if you think about this, you think about my current carrying wire, which I had here, it has a magnetic field around it. If I put that into a permanent magnetic field, then those fields interact and you get what's called the catapult field. We don't need to worry too much about that just now. But this is a thing called the motor effect, because you have a permanent magnetic field, you have a magnetic field that exists already, and that's interacting with the mag field around a current carrying wire. Now we use this thing, we use Fleming's left-hand rule to demonstrate that, and I'm going to do that for you just now. I'm going to sacrifice my left hand here. Okay, so this thumb, remember this thumb is the force. Okay, so we draw a little arrow on our thumbs. I think I do wonder if you tattooed your hand with this, whether they would kick you out of the exam, right? Now the first finger is the field, and it goes from north to south. Now think about it as being in the direction of those field lines, from north to south. The second finger is the current from positive towards negative. Okay, so these are the three things, and they're just directions that are interacting at right angles. Okay, so I could draw them, if I look at my hand like this, I could draw them like this. What would this be? This would be current, this would be field, and this one up here, this would be force. And that's just X, Y, and Z. Now I think where people get confused about it, when they struggle to orientate these things, is the names of those different directions when we describe them on the page, right? So if you think about this X dimension is just left and right. The Y dimension, okay, on the page is up and down. And the Z dimension into the page here is in and out of the page. So those are your descriptions there, right? So you say, well, okay, or I've got a picture of something and there's one coming at the end there. I've got north and south. Orientate, that might be the field going across the page. And I've got a current maybe that's going into the page, and then you can see the force is going down. Okay, so you just need to you know, orientate your hand in any one of those kind of 6 different possible directions that you can hold your hand, and that will allow you to work out the unknown direction. I really like to think about it as this. I really like to think about it as just being like an equation where you've got 2 unknowns and you can work out a third, but instead of working out a number, you're working out a unknown direction. All right. Okay, so hopefully that helps, right? You should be able to recall the factors that affect the size of the force on the conductor. Well, if you just remember, you don't need to remember this actually, you've got the equation. These are the factors. This magnetic field strength, or magnetic flux density, that's B, current, which is I, and the length of the wire in the field. Okay, so those are the 3 things that you don't need to remember them, because you only need to be able to apply them because it's given to you on the equation sheet. Remember, force is going to be in newtons, flux density is the thing that's measured in T, capital T Teslas, current is in amps, A, okay, capital A, and length is in meters. It's got to be converted into meters. Okay, moving on. Electric motors then. So this is really just applying that. A coil of wire carrying a current tends to rotate. This is the base of electric motor, right? So if you think about, if I've got I draw it, a north and a south. Whoops. Got a north and a south. This is my magnetic field then across the page. And into that magnetic field I'm going to put a current carrying wire, but I'm going to loop it round, and the current's going to be in this direction. Okay, so let's deal with this side first. This is, got my hand look nicely tattooed up, north and south. Current though in that direction means that, yeah, this is the field, north and south, that's the current, means that on this side, the left hand side, the force is into the page. Okay, so I'm going to put force in to page, just there. And then on this other side, okay, the current is coming back the other way. So again, north and south, current this way. Now you can hopefully see my thumb is pointing up towards the camera, or in other words, out of the page. So that causes it to rotate. Okay, so you should be able to explain how the force on a conductor in a magnetic field causes rotation of the coil around the magnet. Hopefully you can see that now around in an electric motor. So it's because the currents are going in opposite directions, you have opposite forces on opposite sides of the coil. And what needs to happen then is it needs to switch every half turn, and that's where you have the commutator. Okay, we're almost there. These are the just last few bits of this little topic. Loudspeakers, okay, are really simple uses of the motor effect. Okay, and it's really simple, kind of, you know, it says loudspeakers and headphones. They're just speakers, right? Headphones are just very small speakers. Not they're quiet speakers, but they're just small speakers. So they use the motor effect to convert variations in current to pressure variations in sound waves. This is what you should be able to do. You should be able to explain how a moving coil loudspeaker and headphones work. So this is your explanation every single time. Your first mark is there's an AC signal, that's the first bit, look, an alternating current, and then the second mark is that there is a coil of wire in a magnetic field. So say there's a magnetic field in the coil of wire, the current goes through the coil of wire, and then the third mark is this moves the diaphragm of the speaker, and so you get low pressure and high pressure regions. In other words, you get a sound wave. Now just memorize that, because they're going to come back to that in a moment, because that is exactly the same as a microphone but backwards. Okay, so microphones and loudspeakers, you just remember one thing, but just remember if it goes forwards or backwards. Right, moving on then, this is induced potential. So this is electromagnetic induction. Not to be confused with the bit that we started with at the very beginning, induced magnetism. I think that people do get confused with those two things. In fact, I'm sure that they put those two things in just so they can test out whether or not you get confused between similar sounding words, right? So if an electrical conductor moves relative to a magnetic field, there's a change in magnetic field around a conductor, a potential difference is induced across the ends of the conductor. So basically, if we have a magnetic field and you move a conductor in it, then you're going to get a potential difference. You're going to be able to cause a current. Okay, this is called the generator effect. So the generator is the opposite to a motor effect, right? In the motor effect, we were taking a permanent field and we were putting a current through it and producing a force. In the generator, we're making the force on something and we're moving it through a field, so we're inducing a current. Now the current is opposite to this, okay? The current is the opposite direction, it doesn't matter too much. The induced current generates a magnetic field that opposes the original change, either the movement or the conductor or the change in the magnetic field. So basically, boys and girls, it's just the case that the current that's produced is opposite to the direction of the thing that made it. And that's why we can demonstrate that using that magnet that falls through the copper pipe. I don't know if you've seen that one, but don't worry too much about that. So recall the factors that affect the size of the induced potential difference. That's the strength of the field, the speed of the movement, or the number of turns on the wire. Right, they are the things that change the size of the potential difference. Okay. Now this is the factors that affect the direction of the induced potential difference. So if you take the thing and you move the conductor in the opposite direction of the movement, you get the opposite current produced. If you change the magnetic field around, you get the opposite current produced. So basically you can change the direction of the field or the direction of the movement of the conductor, and that changes the direction of the current. So you should be able to apply the principle of the generator effect in a given context. So that they could ask you some pretty difficult questions then about this, because they could give you a different context and expect you to bring up and apply these ideas. So the ideas would be easy, but spotting them isn't that easy. Earlier on I was talking about the image of the black hole, and that is an example of a difficult context that they could use. They won't use that one this year, of course, but I guarantee that example will come up in GCSE or A level in the next 5 years. Okay, the generator effect is used in an alternator to generate AC and dynamo to generate DC. Okay, so a DC dynamo is exactly a motor but backwards. So if you take this and you don't put a current through it but you spin the coil, then you get a current produced out of the thing. Okay, and you actually get a dynamo. You get DC out of a dynamo, and an alternator you get AC. So it's easy to remember them: dynamo DC, alternator AC. Now the difference is, explain how. Okay, a dynamo has a split ring commutator, and a alternator has slip rings and brushes. So there's good things to remember exactly like that. Right, sorry, didn't see this one. So a split ring commutator, that changes the connection every half turn. If I go back to my little drawing here, a split ring commutator has two like C shapes here, and every single time the thing turns halfway around, it connects to the other side. Okay, but in a alternator, it doesn't do that. In an alternator, I'll draw it over here, slip rings and brushes. In an alternator, one wire is effectively slightly longer than the other, and this wire connects to one ring, and this wire connects to another ring. And they're basically, this wire, let's call it wire A, is always connected to this side, and this wire is always connected to this side. So, okay, and that means you get AC, and you have to be able to draw the graphs of those. So yeah, draw and interpret the graph. So that here it is, look. So I'll just quickly do that with you just now. So this would be DC, this is V, voltage and time. This would be a DC, this would be a dynamo. It does still change, but notice it never goes into the negative direction. That's DC. And AC changes between positive and negative. So you do get high and low in the DC, and that's because it's changing angle between the coil and the actual magnetic field, but you don't get it going into the negative direction. So this AC, because the actual coil A or side A is always connected to one place. Side A is going up and then down, up and down in the magnetic field. So it's going positive direction, negative direction, positive direction, negative direction. Okay, microphones. Now remember I said this was exactly the same as the last one, but backwards. So the last time we said AC signal moves a magnet in a coil of wire, or moves a coil of wire in a magnet. You get high pressure and low pressure sound, i.e. a sound wave. This is the same, but backwards. So you start with the sound wave, talk about the pressure regions if you like, and then that moves a magnet in a coil of wire, and then that makes the AC signal. So you just need to remember that kind of order once for microphone and loudspeakers, and boom, just apply it. Okay, transformers then. This is the last little bit of the electricity and magnetism bit. A basic transformer consists of a primary coil and a secondary coil wound on an iron core. So this is iron core, primary side, secondary side. Okay, you don't need to know about laminations and eddy currents, so don't worry about that. Iron is used because it's easily magnetized and demagnetized, so this basically the magnetic field is going to change inside there. It doesn't actually tell you, does it explain? It doesn't really tell you to actually just explain how they work in this one, but there we go, I'll crack on. The ratio of potential differences across the primary and secondary coils depends on the ratio of the number of turns. Okay, so this is called the transformer equation. And it's basically saying if this is the primary side and this is the secondary, it's basically saying if I have more coils on the secondary than the primary, then I have a higher voltage on the secondary than I do on the primary. And it's in the same ratio as the number of turns. Okay, so more turns on the secondary than the primary, it's what we call a step up, because you have a greater secondary voltage than the primary. If there are fewer turns on the secondary than on the primary, then you have a step down. Okay, in other words, the voltage on the secondary is smaller than the secondary. Okay, so we can remember these things using this simple notation, but really a lot of people find this actually okay. the way I would like to think about it, shall I just do it? I'll just do a worked example really quickly. Okay, let's say I have, I don't know, 100 turns on the secondary, and I have 5 turns on the primary, right? Okay, and I put in a voltage of 6 volts. That's my voltage on the primary. So now I'm going to use this equation, right? Now I just fill in all the things that I know. I know it's 6 volts on the primary. I don't know 6 volts on the secondary. I know it's 5 turns on the primary, oops, and 100 turns on the secondary. So now I've just got one unknown, and now it's a bit different to most equations because normally you'd have only 3 things, but it's a very simple equation to solve. A lot of people like to think about this. Whatever you'd need to do to get from here to here, you have to do to get from there to there. So the relationship between this number and this number is the same as the relationship between this number and this number. So to get from 5 to 100, you have to do times 20. So to get from 6 to the secondary, you also have to do times 20. So 6 times 20 is 120, isn't it? So the voltage on the secondary is 120 volts. That I think is the simplest way around to do it, because you're just putting the numbers in and making those two fractions equal. And I'm certain you can all do that. I'm absolutely certain that you can all make two fractions equal with just sort of mathematical reasoning. Now this is called the transformer power equation. Okay, V times I on the primary is equal to V times I on the secondary. Now this is because electrical power is current times voltage. Okay, so this is the voltage on the secondary and this is the voltage on the primary, and they are equal in an ideal transformer. Okay, so again, it's just a matter of making these two things equal. And this is in an ideal transformer. Okay, so this is if there is no energy loss, which, well, that's never the case, but it's good enough for a kind of model. And essentially the idea is if we increase the secondary voltage from the primary, then we reduce the secondary current because they have to be equal to each other. Okay, now that's really useful in the national grid because is that not in this? It might be in the energy section, might it? It's really useful in the national grid because you waste less energy. You waste less energy if you have less current because current causes heating. Okay, remember to calculate power in watts, voltage in volts, and current in amps. So, explain how the effect of an alternating current in one coil inducing current in another is used in transformers. So this is the explain part, isn't it? And for transformers, memorize this little set explanation then. You get an alternating current on primary. Or in primary coil. You're changing magnetic field in the core. And that induces an alternating voltage or an alternating PD on the secondary. That is, explain how a transformer works every single time. You must say alternating current, you must say changing magnetic field, and you must say induces an alternating PD on the secondary. Okay, if you do that, you can always explain how a transformer works, basically. Explain how the ratio of potential differences depends on the number of turns. That's just using the equation, basically. Or thinking about explaining step up and step down in words. Calculate the current drawn from the input supply to provide a particular power output. That is this transformer power equation bit here, and apply the equation linking PDs to the number of turns in two coils of a transformer to currents and the power transfer involved, and relate these to the advantages of transmission at high potential differences. So why high potential differences is the bit I was alluding to. If you get a high potential difference on the secondary, you get a low current, and if you get low current, you get low heating effect, okay, because this equation you're going to remember as power loss equals I squared R. So low current, less heating effect. Now, although I'm finding this really, really useful, I'm finding it's taking me longer than I was expecting it to do. So I think what I'll just do, if it's all right with you all, is I'm just going to look into the chat quickly. And there's some nice things here. Can I cover the whole of the specification like this? Well, it's taking me quite a bit of time. I hope that's useful, but it's taken me quite a bit of time so far. What I really should have done, I guess, is called this just one topic and then sort of ditched it and come back to another time. Sarah, what's the best way to memorise the formula? It's memorise equations for GCSE Physics. Of course it is. It's this book that I sell, which you can buy from the link down in the description. I think it's really useful. It's a bit like flashcards. It's kind of pocket sized, and it gives you ways to use them as well as gives you practice using them as well as just memorizing them. Remember, don't memorize them as triangles because you won't get the mark if you just memorize them as triangles. Yeah, but you don't need to talk about the paper cone, Sana, though. Yeah, so you don't need to. The paper cone is not going to get you a mark necessarily. Variation currents make the cone vibrate, which makes the air around the cone vibrate and creates a vibration in pressure that causes sound waves. That's not bad, but you didn't get the coil of wire in there, Sana. Okay, so you need to say makes a coil of wire in a magnet move, right? Physics is a bit difficult, yep, but you know, it's worth learning. It's a fantastic subject to learn. The message at 1535 wording is a bit confusing. Okay, I'll have a look at that. WWUE plug. Does it make sense? Frequency of a sound wave is the same as frequency of alternating current. Yep, absolutely, that's fine. This is helpful, that's great. I'm glad. Perfect 6 markers for speakers and microphones, thanks. I think I've already got one actually in my OCR Gateway explain videos. And people drawing, yeah, I would definitely draw that on your hand. Just like as a wanna, just to remember it. Other people like to remember it as F, B and I. So force, current, force, field and current. F, B, I. I'm gonna drop this feed. I'm really sorry to say, because I've promised people A-level feed at 4 o'clock. So I'm just going to go and spend 10 minutes just getting ready for that. What I will do, I don't think I'm going to have time to come back again today, okay, which is going to be really disappointing. But I will do a feed which will probably have the title electricity, and I will go through the electricity part of the spec in the same way if you guys are finding that useful. I hope that is okay. Sorry that father, mother and child, that's quite a nice one. I've not heard that one before. So force, no, that doesn't, how does that one work? Thought? No, because M would be the movement, wouldn't it? So it's not in the right order, but okay, whatever helps you to remember that. But don't forget to remember the directions of the things as well, which is why kind of drawing on your hand helps me, because I can always imagine those north and south and positives and negatives and things like that. So thanks a lot for watching. Thanks a lot, GCSE students. I'm going to drop the feed just now. I'll promise you a live feed in the future. Oh, force, magnetic and current. Yeah, that makes sense. Okay. I don't know why I didn't get M from that WWE plug. All right. It's been great spending time with you this Easter, GCSE students, and I will see you again real soon. I owe you some live streams, okay, coming your way for electricity and for hazards and uses of radiation in medicine. Thank you so much for watching. It's been a real pleasure. All right.